Let's suppose that at some time t, a particle is in this position on a circle of radius r. Let v of t be its velocity vector at this instant. We know that the velocity vector is tangential to the circle. We know from previous videos that if the particle is moving with constant speed v in a circle, then at any instant the acceleration vector points towards the center of the circle and has magnitude v squared over r. Now, let's suppose that instead of uniform motion, the particle actually speeds up, so that after some small increment of time, delta t, the speed has increased. So now I'm showing the velocity vector at the time t plus a small increment delta t later. You can see that the magnitude of this vector is greater than the magnitude of this vector here. Let's suppose that during the time delta t, a small angle delta theta is swept out. To get the average acceleration vector over the time delta t, we need to get the change in velocity over that time, delta v. So, as we saw before in the video on the situation of uniform circular motion, we just have to subtract these vectors to get the change in the velocity. So we put the tails of the vectors together, so we move them parallel to themselves with the tails together. We join the head of vector v of t to the head of vector v of t plus delta t. Okay, so delta v is just v of t plus delta t minus v of t. For the case of constant speed in the circle, we knew that these two vectors had the same magnitude or length. So let's just look at the case of uniform or constant speed again. We would have had two vectors like this here, and to get the change in velocity we would get this vector here. We saw in the limit as delta t and hence delta theta approach 0 that the direction of this vector will approach a direction pointing towards the center of the circle. Now that's not going to be the case here. As we let delta t and hence delta theta go to 0, the change in the velocity and hence the acceleration vector will point to a position below the center of the circle. Now we can think of delta v as being made up of two components. One component is the change in velocity that we would have gotten if the speed was constant. Both velocity vectors had the same magnitude. Okay, that's this component here, and that's the component that we're interested in. Let's consider this angle A that is in here. Now, we saw in the previous video for the case of uniform circular motion that this angle here, the angle between the initial velocity vector v of t and the change in the velocity, well, this would have been the change in velocity for uniform motion, this angle approaches 90 degrees. That's what we saw. And since we have an isosceles triangle here, this angle here also approaches 90 degrees. Which means that angle A indicated here will approach 90 degrees. To get the acceleration at time t, to get the acceleration vector, we have to take delta v and scale it by 1 over delta t. So that's just a scalar dividing by a scalar, and take the limit as delta t approaches 0. That gives us the acceleration at this time. But of course, when we take this limit here, this component will point towards the center of the circle. Okay, now the other component will point perpendicularly to the radius line, and we're not interested in that. So I'll show those components after we've taken the limit. So these components will be at right angles to each other. As I said, this angle A will approach 90 degrees. Now this is the component that we're interested in. For the case of uniform speed, we know that the acceleration vector has magnitude v squared over r, where v is the speed at this instant and r is the radius of the circle. Now, we are not going to be interested in the other component of the acceleration vector. The important point in this video is that if we resolve the acceleration vector of a particle undergoing non-uniform circular motion in a direction along the radius line, then that component will point towards the center of the circle, not away from the center, and its magnitude will be v squared over r. Now, what about the resultant force on this particle? Well, the resultant force on any particle by Newton's second law is in the same direction as the acceleration. All we do is we multiply the acceleration vector by the mass, so we scale the acceleration vector. So again, of course, the resultant force is not pointing towards the center, but be pointing somewhere below the center for the case of a particle speeding up as it moves clockwise down this part of the circle. So this F is the resultant force at this particular time. I should really put T in here. Now, what about the component of this force along this radius line? Well, we just project the tip onto it, and it's easy to get because all we have to do is scale up the corresponding component of the acceleration vector. Scale this up by a factor of m. Well, scale it up or scale it down depending on what m is, if m is greater than 1. But anyway, it's going to be in the same direction as the component of the acceleration, but its magnitude is going to be given by m times this, as we multiply m by the acceleration to get the resultant force. So we multiply m by v squared over r. So we're familiar with this. This is the centripetal force for an object undergoing uniform circular motion with constant speed v. Now, in the next few videos we are going to be looking at examples of particles undergoing non-uniform speed, just like in this case here. We will be dealing with objects that are speeding up. So the resultant force vector will not be pointing towards the center. But we are not going to be interested in the resultant force vector. We will be interested in its component along this radius line here, and we know it's the magnitude of this component. We are not going to consider the other component.